let's have now the example. Find I/O using Thevenin'S theorem. I/O in the circuit is the current that is flowing through the 10 ohm resistor. So let's have the first step. Let's recall that in solving for the Thevenin'S theorem, our goal here is to have the values of the VTH. This is the VTH and the RTH. Okay, so we have to convert a complex circuit into a simple series circuit. The terminals A, B, it is where the RL is to be connected back. Okay, and RL here, what is RL? Since IO is the current that is flowing through the 10 ohm resistor, RL is equal to the 10 ohms resistor. And IO is just equivalent to RL. Okay, so our goal here is to determine the series combination of VTH and RTH, the values of the new source voltage of the VTH and RTH. So let's have step 1, find RTH. So let's recall how are we going to solve for RTH. We'll have to remove RL. And what is RL here? Which is the 10 ohms. Why? Because the unknown is the current through the 10 ohm resistor. Remove RL and leave the terminals open, and then set all independent sources to 0 and draw the equivalent circuit. So we have the voltage source replaced by a short circuit. Then we have here the 1 ohm, then the 8 ohms, and this is the RL. So let's remove it. And we label the terminals as AB. It is where the RL is being disconnected. And the current source be replaced by an open circuit. Okay. Now, since in the open circuited terminals, no current flow, so it can be neglected. If we have to redraw the circuit, the 1 ohm and the 8 ohms are now connected in parallel. So this is 1 and 8 ohms. And then it is here the open circuited terminals. It is here we are going to solve for the RTH. And the 5 ohms. Okay. So what is now our observation? So we have our observation here that the 1 and the 8 ohms resistor are connected in parallel. So we will call this as the RA. And RA is just equal to 1 over 1, or simply 1 over 8. Or that is equal to, if you compute, you have that value. Okay. Now, if we will simplify the circuit, so let's redraw the circuit again. So since we combine the 1 and the 8 ohms, and we call it as RA. And we have this terminals AB and the 5 ohm resistor. It is where we are going to solve for RTH. We observed that RTH is just simply equal to the series combination of RA and R5 and 5 ohms. So it is RA plus 5. If you compute for RA, then add it to 5, that's equal to 5.8 99 ohms. Okay, so then we have already found the RTH. Our step 2 is to solve for the VTH. So step 2, solve the new source voltage, which is the VTH. Recall that in solving for the VTH, we need to disconnect only the load 10 ohms, and take note that all sources must be still connected in the circuit. So we have to disconnect only the RL, and we call these terminals A, B. And then we have the sources connected at the terminals. Let's draw the circuit. And then we have here the 8 ohms, and then 1 ohm. Okay, and then we have the 5 ohm resistor connected in parallel with the current source, the 2 amperes. Okay, it is where we have to solve for the ETH at the open circuited terminals. Okay, what is the sign of the ETH? If we go back to our circuit, so the current IO, it is assumed here to the right. So the current IO leaves plus at the 10 ohm resistor, then you have here minus. If we have here the A, B, so at the point A, we have plus, and at point B, we have minus. So we have here point A plus and minus at point B. Okay, now, if we look at here, we have two independent sources, the voltage source and the current source. So how are we going to solve for the ETH? Of course, since the circuit has two independent sources, then we have to use any network loss and theorems that we discussed. So we have to integrate another network loss and theorem. So if we decide to use mesh analysis, so we have to assume mesh current. So we have current I1 here and current I1 here, and then this is I2. Okay, and remember here that the current, if we have a current I3 here, the current here is equal to 0 since it is an open circuit. So we don't need to solve for IO since I3 is equal to 0. Okay. Now, at loop 1, so we write the voltage equation. So by following the direction of the current I1, so we have 12 minus 1 times I1 minus 8 times I1. And since there is no current flowing in this loop, no, the I3 is 0, so we just have to equate it to 0. So therefore 12, then to simplify, we have minus 9 I1 that's equal to 0. So we can solve for I1 that is equal to 12 over 9 amperes. And then at loop 2, the current here is I2 is just simply equal to 2 amperes. Why? Because the loop current I2 has the same direction with the 2 ampere current source, and there's only one loop current that's flowing into it. So simply I2 is just equal to 2 amperes. And we have to solve then the ETH. Now, if we have this node as A, this one as B, then this is C and D. Okay, and then if you write the equation, so KVL at loop A, B, C, D, A, assuming in a clockwise direction. Though the current here in this loop, the I3 is 0 because it is an open circuit. There is an open circuit in the loop. So there's no continuity of the current. So the current is equal to 0. But still there is a voltage available at the open circuited terminals. So if we use KVL to write the voltage equation, so in a clockwise direction, so we have minus E TH. And then the voltage at 5 ohms. So what is the current that flows through the 5 ohms? So when the current I2 passes through 5 ohms, it's going upward. So we have plus and minus. Of course, there is no current in this loop. I3 is 0. So the only current that flows through the 5 ohm is I2. So when we write the voltage equation in a clockwise direction, so we see the plus sign of the 5 ohm plus 5 I2. And then next we have at the 8 ohm resistor when the I1 is flowing into it. So we have plus minus. Again, there is no current I3 that flows through 8 ohms because there is an open circuit. I3 is 0. So when we have to write the voltage equation at loop 3 or A, B, C, D, A, then what we see is only the voltage drop of 8 ohms due to I1. And we see here the plus 8 I1 equals 0. So solving for ATH, when we transpose it to the right side, then ATH is equal to 8 I1 plus 5 I2. Okay, if we substitute the values, I1 is 12 over 9 and I2 is 2 amperes. Then the value of ETH, if we solve it, that's equal to 20.667 volts. Then, since we already have the values of RTH and VTH, then we draw the equivalent Thevenin equivalent circuit. So we have the new voltage and new internal resistance. So the VTH now, this is 20.667 volts. And the RTH is 5.889. So you have 5.889. And this is the terminals AB where we have disconnected the RL. So the values of the voltage VTH and the RTH, these are the values when we removed the RL or we excluded RL in the computation. And then we will connect back the RL to the circuit. RL is equal to 10 ohms. Why is it that the RL is equal to 10 ohms? Because it is where the IO flows. The IO is the unknown, so we have to consider the RL that is equal to 10 ohms. So this is IO. So how to solve for IO? IO, just use Ohm's law. So you have 20.667 5.667 divided by the RTH, which is 5.66. Okay. It's 5.889. So we'll change the value. So it is 5.889. 5.889 plus the RL, which is 10. So the value, if we solve it, that's equal to 1.301 amperes. Okay, that's how to solve for the unknown in a complex circuit using Thevenin's theorem.